it's completely automated. So how is the operator understanding what we are saying? We have our different dialects, we have our different accents, we speak with different fluency. So the machine should be able to navigate through this diversity, and it's able to very accurately predict or infer that this is what the speech is about, and these are the different sources that are present in my speech. Again, speech recognition, very, very important problem. Activity. So here's this very data set which are now dynamic frames. Now these are video images. There is activity happening. In one image, child is playing. In some other image, there are two people who are talking on a table. In some other video, there must be some person who's walking, dancing, doing an exercise. So I want to not only segment the objects in the image, I want to segment the activity that they are performing in the image. So I give it an image, this is a video image, so there are multiple images in a frame, so it's a dynamic frame, and it tells me what are the objects in that image, so that's semantic segmentation. What is the object doing? Is the person walking? Is he doing exercise? Is he doing like push-ups or whatever? Is he eating or watching a TV or something like that? There is some activity that is in those images, and I want a machine learning algorithm to tell me what that content is all about. So that's basically video recognition or video. Then there's face detector. So this is probably one of the largest selfies that has been acquired. And what we want to automatically extract faces of people. And we can see that the people in the front row, they're perfectly visible. Their whole facial structure is there. But as we go deep into the image, we can see that most of the people's faces are kind of semi-occluded by people in front. So there's an occlusion problem or a semi-occlusion problem. There's loss of resolution as I go. So these are quite so I want to have a face detector tool that can automatically crop out the faces of the people in these images. And again, this is a security application. Your camera is acquiring this dynamic activity in the entire 24/7 period, 24 hours and 7 days period, to automatically ask that algorithm to tell you what are the sorts of people that are out there. Are there some people who are questionable people who shouldn't be there, or is somebody trespassing or whatever. So I want to understand a very simple thing. How many men and women are actually entering a facility? What is the demographic that is coming there? So it's a very, very simple problem. Face detection, or you can also talk about as Facebook tagging, that I want to tag. And again, there's another one which is object detection. So it has like close to million boxes, so 50 million images. There are 100 categories, and there are 30 million labels in it. So again, I'm trying to identify the objects in the images, and I'm trying to put, is there a cat there? Is there a rabbit there? Is it a table there? Is it a chair there? So I want to segment all these objects, and again, into multiple categories, and it's again a multi-label, multi-object detection problem. Very difficult for one person to go through each collection of data set as automated as possible. So the last one I'll talk about is from my field, which is basically brain tumor segmentation. This is basically diffuse low-grade gliomas. You see images of various patients, and clearly see that all these tumors have different presentations. They occur at different spatial locations. They have different sort of expression, and it's very, very difficult to perfectly segment this tumor or tumor substructures from these images. And it's a very, very difficult problem. Like, it's very difficult to say if this is tumor or there's just some intensity, normal intensity, non-physiologic variation. It's very difficult to actually answer this problem. So we have these sorts of problems both in computer vision, machine learning, and in where solve these very, there are immense value, immense segment. So some of them are out there, not all. There are many, but some of the applications are cover a good gamut of subjects that most of them. So talk about, so we are hearing these terms like artificial intelligence, machine learning, and deep learning. And sometimes we believe that these terms are quite interchangeably used. So there's an abuse of nomenclature there, but it's always good to understand, and I'll make a what is the difference between these three disciplines. Usually this picture makes in our mind when we are talking about machine learning is the machine which is like participating in a class lecture and is taking notes and it is learning or something like that. So this could be a very, very literal meaning of what we think as machine intelligence learning to be. So right now so artificial intelligence is basically any form of technology. It could be computers, it could be something more different than computers, it could be any device that can have some sort of a pseudo-intelligence mechanism that we can call it as some sort of an intelligence thing. And within this AI, when I'm talking about a very specific group, let's say computers, it becomes machine learning. So machine learning is a very special class of artificial intelligence that actually looks at a very specific technological group and its associated learning aspects, its associated intelligence aspect. And when we're talking about deep learning, it is a specific technology from that group that we are talking about. And again, and its associated intelligence aspects, how that technology actually acquires knowledge, how does it learn from its data, and that's what we have. So we have a deep learning, which is a subset of machine learning, which is further a subset of artificial intelligence. And one question that why do we even need about this thing? What is important in this? And it is very important. And these are basically summarized by these categories. So what is it artificial that will be manifested in deep learning also? That's very, so whatever fundamental, I'm not very, so fundamentally whatever good, whatever virtue artificial intelligence possesses, that virtue will be shared by any member of deep learning also. Likewise, if there is any fundamental limitation that is in artificial intelligence, the fundamental limitation will still be a problem in machine learning, will still be a problem in deep learning. So that is why we need to understand what machine learning is. So it's very difficult to just leap to deep learning directly without understanding what are the underlying limitations and virtues of machine learning that I need to know, because they are going to show up. They are going to express themselves in my deep learning problem, in my deep learning solution, and I need to be aware of that. So we are going to spend time trying to understand what are the fundamental limitations of machine learning, which are fundamentally in deep learning. That's very, very important. So that's why we need to understand what machine learning is. So if we just have a very machine learning, it's a model that, that's it. So you have a data set, and that data could be documents, videos, audio signal. When I say videos, it is a dynamic image. When I say static image, it's a static frame, 2D frame or a 3D frame. It could be bioinformatics data, it could be genomics data. So it could be anything. I have data, I want my machine to learn knowledge from this data and be able to do some inference on some unseen data. That's what I want to do. I want it to perform some tasks. And with every data, we have some dimensions associated to it. So we are going to assume that we have n examples, n instances, and each example is a d-dimensional vector. So now I can say that, okay, my x is basically a matrix. That's why I said it's matrix analysis in linear algebra. It's n by d. So the rows are indexing my example. And the columns are basically the different components of each of this example. So it's an n by d matrix that I have. And we are living data, so which means it will be large and large t. It is in millions, d in billions. That's what big data is. And just most of the time, so the complexity is basically of the order of n times t. So it's humongous. So that's basically large scale machine learning. So you have millions of examples, and each example is a high dimensional vector in some million dimensional space. So it's a huge problem, and maybe 30 years ago, 40 years ago, it was not possible because of the limited computational resources, but now we have big data and we have the technology to back it up. So when we talk about learning, so we can think about us, and I think all of you have seen these kind of diagrams in calculus when we were studying functions. It's as simple as that. We have a bag which is basically represented by this x. It has a collection of points, call it my data points. And each data point has an associated, there's some label, there is some value that has been assigned to it. It could be like the people in the, and this could be the age of those people. It could be the height of those people. It could be anything. Have a collection of objects which is input set, you have a collection of objects that is called the output set. I want mapping. I don't know the mapping. That's what I want to learn. That's what I want. So the very, very first learning, as far as I can understand, that all of us did was that we actually did in our labs this Hooke's law experiment, where we said that the force is directly proportional to extension. We measured, we applied different forces, we measured some extensions, and we just plotted those data points on the graph. And we fit the line, the best line that fits through the graph. And there were these points, some were on the line. So what we were doing, we were trying to learn a model. And this model was basically a linear model with a slope and an intercept, parameters that I want to estimate. So in this case, I don't need machine learning. It's a very, very simple problem. It's not a large scale problem. It's a problem that we can do even on a piece of paper if the numbers are not that ugly. There's no square root of 2 or square root of 1000 or square root of 13 or something like that. But we can do it on a piece of paper, and they're analytical closed form solutions. So there's a function. So in some cases, this function is very easy to find. In many cases, it's very, very difficult. So what this function is. And we want the machine to learn this mapping between the input data and the output. And that's what machine learning is all about. So we are trying. It's a very, very simple example. So mathematically speaking, we have these pairs of points. So each example has an associated outcome, and we are assuming they're independent, identically distributed. Each example is a d-dimensional vector, but my outcome, assuming, is a scalar. It's not. It could be multi-dimensional outcome also, but right now for simplicity, each d-dimensional vector is only assigned one real. Plus minus 1, it could be 0, it could be 3, 3.3, pi, whatever. It's just one value. So that's what we have. So we are trying to learn